Okay. So welcome to our last concept lesson for the chapter, and this is Gauss's law with dielectrics. We've already learned Gauss's law, but honestly, most of nature is not in a vacuum. So maybe it's time to discuss the real Gauss's law. Okay, so we'll start with just a simple parallel plate capacitor. We're going to review Gauss's law before we try to refresh it and upgrade it. Okay, so imagine two metal plates, one with a charge positive Q, one with the charge negative Q. So I have here a drawing of the top plate especially. I'm most interested in the top plate, and the space between the plates is vacuum. Like there's nothing there. All right. So what I've drawn here is a Gaussian rectangular box. So I'll show you how I created it. I decided to take, for my G surface, a box like this, a rectangular solid. And that rectangular solid has its top face up against the top plate. So it's under the top plate. I just shaded the top capacitor plate. Okay, so this is a close view. And actually, I'm going to push the G surface up a tiny bit more until its top surface is inside the plate. I love the inside of a plate because there's no field there at all. I love that about conductors. I usually try to put part of my G surface inside of a conductor. That way it minimizes my flux integral amount of work. Do you guys remember Gauss's law? It's been a while. I'm going to put it up on the board again. Here it is. Right here. Does this look familiar? This is Gauss's law. Okay, so Gauss's law requires us to do epsilon naught, that's the vacuum permittivity constant, times the closed integral of E dot dA, and this promises to give us the charge enclosed. Remember this law? It's a vector law, unfortunately, but it is under a dot product, so it does turn scalar on us. Okay, this law needs to be upgraded because, frankly, epsilon naught is not the typical reality of our universe. Most things are not in vacuum, you have to admit. Even air is a dielectric, technically. All right, so we're going to try and upgrade this law. And so going back to my picture, I'm going to assume that my G surface has as its top surface, buried inside the conductor. That's to prevent any field flux through that top face. Also, the sides of the box are perfectly vertical, and so are the field lines. So that means I won't get any flux through the sides of the box. So even though my box has 6 faces, a top and a bottom, a front and a back, a left and a right, I don't have to worry about 5 of those faces. So anything I'm shading in blue has 0 flux. Front and right, back and left. I should have said front and right, back and left, and then the left, this front side here. None of those have flux. Only the bottom surface has flux. So down here, this green face, the bottom of the box. So I'm not sure I said that right. So you see how I color-coded this. The G box is in red, and the bottom face of the G box is in green. So I purposely highlighted that in green. And since my closed integral is really supposed to be an integration for all the surfaces, and since I'm not going to be discussing all the surfaces, just the bottom surface, I'm going to remove the little circle from my integral. So you probably remember we used to do this quite a bit. So we would take the epsilon naught times the closed integral E dot dA, and that upgrades to epsilon naught EdA cos 0. I'm saying cos 0 because both the area vector and the field vector are aligned. Okay, so remember, whatever G surface you make, right, your area vector points normal to the surface and always points away from the interior, right? So in both math and physics, we always make our normal vectors point out of the closed object. We never poke them into the closed object. That would be called a negative oriented surface. We don't deal with that in this classroom. Okay, so what I'm saying is on our G box, both the field vectors fluxing through the bottom and the area vectors are aligned perfectly. So we have cosine 0, and we're obviously neglecting the fringing, the bending of the field lines, near the edges of the plate. Okay, so cos 0, of course, is 1. So we don't need the cos 0. Also, the E pulls out. And the reason the E pulls out is because as you traverse along the green line, you don't experience any changes in E at all. So as you travel along this green, there's no change in E. So the E is non-dependent on the area. And then since the area that we're interested in is just the bottom surface of that box, which happens to be the area of the capacitor plate, we can just replace integral dA with A. In other words, integral dA is just A. A means the area of the capacitor. Okay, now, usually I want to isolate something. So in our Gauss's law, if you're looking for field, you isolate field. If you're looking for charge enclosed, well, it's already isolated. We are actually looking for field, so we would write it like this. Okay, you've seen this before, except it didn't have an A on the bottom. In fact, what we did, if you remember, was we said that Q enclosed is just sigma A. And we actually replaced the numerator with sigma A and the A's canceled. So this is what should look familiar to you. It is the area, or sorry, it is the field near a conductor, a flat conductor. You've seen this formula before. I am not teaching something new. I'm refreshing Gauss's law, like how we do it. So it's basically draw a G surface, calculate the flux through all 6 faces or however many faces you have, simplify it down. All right. What happens when you put a dielectric between the plates? So what if we put in a dielectric? That's the question of the day. Very important question. So same exact scenario, but we put in an actual dielectric. So the dielectric is represented by this blue here, and it could be water, it could be ceramic, could be porcelain, could be strontium titanate, whatever it is. Remember, there's different kappa values for these things, and although some are really good at raising up the capacitance, they sometimes do break down under low voltage. So, even a small voltage can ruin the dielectric and make it into a pure conductor. So you probably don't want to use the same material for every application, even if your favorite is strontium titanate, which has a kappa value of 310 or something high. All right. Water seems to be, just looking at the table in our book, this is just a side note, but I noticed something about water. It has a very high dielectric constant, not as high as strontium titanate, but it has a very high dielectric constant anyway. And it looks like the colder the water, the higher actually. So the temperature of the water might matter too, Okay, so anyway, that's interesting. So now the question is, what happens to Gauss's law? And actually, it's a very simple thing, but it takes a while to realize it. So we're going to kind of run through this derivation here today. That's our job. Okay, so the first thing is we're still drawing the top plate only. We're only considering the top plate. So what you see here is a picture of the top plate. And remember, the top plate is made of metal, usually, or some conductor. So the charges congregate to the edges. So you guys remember that from the rule that there's no actual field inside, right? So just kind of ignoring the G surface, all your charges collect on the surface, right? Now I'm going to draw them inside, not because they're inside, but because I need to draw something under this black line in a minute. Okay, so when we fill this with a dielectric, it looks like this. So the blue is the dielectric. Now, why are there all of a sudden negative charges here? Where the heck did those come from? why all of a sudden are there these negative charges? Where'd they come from? In the previous picture, they weren't there. All of a sudden, boom, we got two types of charge going on at this surface, the bottom surface of the capacitor plate. What the heck just happened? I'm going to pause the video and see if you can tell me. So a student said that the negative charges are actually induced. They're actually caused by the positive charges. So, and another student suggested that I maybe move these down a little bit. So let me shrink it a little so it fits. All right, oops. So we have basically positive charges on the plate and negative charges that congregate from the blue medium. They actually came from the molecules in the blue dielectric, and they're trying to approach these positive charges that are on this plate. So what's going on is one of two things. Well, we'll get to Gauss Law in a minute. In the dielectric, there's two possibilities. Either this dielectric is like water, right? Let's say the dielectric is water, and a water molecule, remember, looks like this. You've got two hydrogens, right, and an oxygen. This is a crude drawing. The oxygen is way bigger. It's, totally different mass than the hydrogens. But you know that hydrogens are just like bare proton, pretty much. There's just a proton with one electron. So what ends up happening is this side becomes more or less positive, and this side becomes more or less negative. This is just a naturally occurring dipole in nature. Like, you don't have to create these things. This is water, folks. Okay? And we said there's a 105-degree angle between them. So you guys remember that water is a natural dipole. Okay, so let's say that this material is water in here. So what ends up happening is those water molecules then align themselves with their oxygen facing up. So this would be like this. The oxygen would be here. The hydrogens would be as far away as they could be from the top plate. So what happens, though, is this creates another field that has nothing to do with the plate. The plate field is coming down, but the little dipoles themselves are producing their own little upwards field. So what ends up happening is the little blue field, which comes from one water molecule, ends up canceling a bit with the plate field coming down. And remember, there's billions of these water molecules. So even though each one has a very, very tiny contribution to an upwards field, with a lot of water, you could actually have quite a significant decrease in the black field when you take the vector sum. Doesn't matter. All right, so since this is pointing up and there's many of them, and there's only one pointing down here, or there's already a field pointing down, then you're going to get a lot of somewhat canceled field. Diminished E means diminished potential. Diminished potential means increased capacitance. Okay, so that's one possibility. This is called a polar dielectric. It just means that inside our dielectric, we have naturally occurring dipoles, and all they have to do is quickly align themselves to their state of comfort, and we increase our capacitance. That's one type. Another type is nonpolar dielectrics. So there's another way this can happen, even if it isn't water, even if it's made of something non-dipole-like. Okay, so I'm going to erase this water molecule here. And let's go to a more general situation. Because, not every naturally occurring molecule is an effective dipole. They probably all have some dipole moment, but not as big as water, perhaps. Okay, so imagine another molecule, and it doesn't really, I don't want to draw its substructure, but it doesn't have like a strong dipole moment of its own. So what happens when you put it in this field? Well, it's going to stretch itself. So it's going to first look like that, but then it's going to stretch itself a little bit. And the center of charge caused by the orbiting of the electrons and the positions of the protons relative to the electrons, all that, it's gonna basically distort. And so the center of charge will shift, making this like a stretched molecule, so to speak, or the center of charge shifts a little. This is a much weaker phenomenon, but it is a real phenomenon nonetheless. Now we have that same issue with the arrow pointing up and there are many of these molecules canceling the field and increasing our capacitance. Okay, so that's called a nonpolar situation. So polar just means it's already made of a dipole material, and nonpolar means you're basically forcing the molecules to look like dipoles for just a slight effect. Okay. All right, so those are the different situations we could have. Let's look at what Gauss's law actually looks like. So our G surface is the exact same G surface we had before we put in the dielectric. The bottom surface of the G surface is still the only surface with flux. The field lines from the plate are still downwards only. Okay? The field lines from the top plate are still perfectly aligned with the area vector. So nothing has really changed except one small thing. Now we have two enclosed charges. We have two enclosed charges. And I'll follow the student's suggestion, put these little pluses down under the plate, because no net charge should ever exist inside a conductor, Mr. Shore. Okay. All right. So you'll notice there is actually two charges enclosed, positives and negatives, if that makes sense. Okay, so I'm going to label the positive charge that's enclosed. I'm going to label that thing plus Q. And for this negative charge that's enclosed, it's negative Q prime. The prime means it's much smaller in amount than is the positive. Okay? By the way, there is also another distinction that you should be aware of. The plus signs that you see here are mobile, meaning if you remove the battery, right, or if you change which battery you're using, whether you increase the voltage or decrease the voltage, you will either gain or lose pluses here. But the negatives are kind of there because the pluses were there. They are part of the molecules in the blue. So even though the pluses are more mobile, the negatives are sort of just fixed in the goo. They might return back to their state of peace when the top plate is no longer positively charged, but they're not free in the same sense as the top pluses are. Okay, this is especially obvious if I had used a minus. I should have used the bottom plate for this argument, but if this was all big minuses and these were all little pluses, which is the way the bottom plate looks actually, those minuses would represent electrons ready to escape down the wire whenever the capacitor is connected to a circuit or whatever. But the ones underneath, the ones in the blue, or the ones more in the blue, are there to stay. They're part of the molecular structure of the dipole. Okay, so they do call the top set here free charge, and the bottom one, those are more bound. They are already part of atomic orbits and stuff. Well, they all are, but anyway. So that's kind of what we call free charge versus the bound charge there. Now, when you apply Gauss's law, then the only difference at all is that your Q enclosed now is Q minus Q. In other words, everything is exactly the same. The left side is still epsilon naught EA, but the right side is now a little bit diminished because the enclosed charge in our G surface is slightly lessened now. And I changed the color of my box a little. My G box is right here. And I don't need this up here. This is, I should erase this thing up here. That's the top of the top plate. We don't need that. Okay, so anyway, not the best drawing. But all I'm saying is that the new Gauss's law looks like this. Now here's the thing. I don't really want to worry about Q prime. I don't like Q prime. Q prime kind of showed up. And I don't want him in my formula at all. So here's what I'm going to do to get rid of Mr. Q prime. First thing I'm going to do is rewrite the E field when the dielectric is placed in. So I'm going to isolate the E. So this, the first thing I'm doing is isolate the E. I did this, remember before we put the dielectric in, I had isolated the E also then too. So I always like to isolate my E if at all possible. Isolated my E. And then comparing this to the other page we had earlier when we did it without the dielectric, now we have two formulas. We have the E field when the dielectric is in place and the E field when the dielectric is not in place. The only difference is what? What's the only difference? Okay, now in yesterday's lesson we said one more thing. We said that the E field is diminished. The E field with the dielectric is E field without the dielectric divided by kappa. Remember, kappa is bigger than 1, so when you put it in the bottom there, you do lose a little field. And that's why it's E over something slightly bigger than 1 is going to be something slightly bigger than E. Okay, so our Gauss's law without a dielectric look like this, right? Q enclosed. This is without. And the Gauss's law with the dielectric looks like this. The Q enclosed is now a Q minus Q prime. And if I take these two top equations up here and I divide them, if I just divide them, I learn that E without divided by E with is Q over epsilon naught A over Q minus Q naught, Q prime over epsilon naught A. And then the denominators of the denominators cancel out. Okay, and so right here, E without stays on top. E with is E without over kappa. And this is equal to the simplified right side. And then the E without cancels. And we get kappa equals Q over Q minus Q prime. And isolating the Q minus Q prime, we have Q minus Q prime is Q over kappa, which will replace the right side right here. Okay, so the new Gauss's law is epsilon naught closed integral of E dot dA, and this is E with a dielectric now, equals Q over kappa, or we could bring the kappa to the left side. And here's the question, should we put it outside the integral or should we put it inside the integral? That's a very important question. This is what you would use if kappa is truly constant throughout the dielectric. Throughout the dielectric. Okay, however, if you want to bring the kappa into the integral, that's even wiser. And this is nice in case your kappa is a function. Sometimes your kappa is non-constant. For example, you might have a strontium titanate, right? And it's got various densities throughout it. So if that happens, then your kappa depends on the where you're at along the plate. Maybe that's the right thing to do, to build your capacitor to have a variable type kappa. And if that's the case, you'd want that in the integral because it would affect your integration step. Okay, so this is like the most formalized, most versatile, most powerful Gauss's law we have, minus any error correction terms and stuff. But this guy here with the kappa inside allows us to really put in any material we want, and allows us also to just vary it even, spatially, like have different kappas in different parts of our capacitor. Okay, just a quick little side note. I've noticed some textbooks, and I'm really glad our textbook doesn't do this, but some textbooks will take the epsilon naught and the kappa, and they'll glue them together, and they'll just call that epsilon. I do not like this notation for two reasons. First of all, it makes it appear that the little sub-zero is super duper important. Like a lot of students forget to write the sub-zero, right? And now all of a sudden it means something totally different. So I don't like that, how that subscript holds that much power over us. So I will never simplify epsilon naught kappa to be called epsilon. The other reason is this is supposed to be a permittivity constant. It's supposed to be a natural constant of nature, like I'm saying. You know what I'm saying? So if we connect it to k like this and just call it all plain old epsilon, then epsilon is no longer necessarily a constant. It depends on whether or not your kappa is a constant, see? So kappa doesn't have to be constant. You can allow your capacitor to have multiple kappas in it, but you don't want your permittivity constant to be non-constant. So I will never use this notation, even though it is tidier, but you will definitely see textbooks where there's epsilons and they are not epsilon naughts. You have to be aware that's kappa epsilon naught, technically. Okay, this also happens with index refraction in optics and other subjects. Like they'll just switch it up and just switch the letter or drop the subscript. And like E1 might be permittivity in air, and E2 might be permittivity in water, and epsilon naught is permittivity in vacuum. You see what I'm saying? So I will never use that notation. Okay? I don't like the way it's so picky with the naught, and I also don't like how it makes epsilon naught suddenly possibly variable. It's supposed to be a constant of nature. It's the same reason I would never take the old k, which is 9 times 10 to the 9th, and glue it to q. Yeah, there's kq over r, that's potential, but I'm not going to call kq something new. K is a constant of nature, and q is a property of this problem, if that makes sense. So I won't put those together, although I used to do it all the time. All right.